So this is the 18th session in the subject of digital communications, and we are going to study orthogonality between sine and cosine, and also how to generate signaling waveforms using sine and cosine called as quadrature amplitude modulation signals. That is what we are going to study. So first what we'll do is we'll find the condition which will make sine and cosine terms orthogonal to one another. Also see what should be the amplitude of each of these signals so that they are orthonormal as well, and then take the study from there. Alright, so let us start. Let us state the problem first. So let's say we are given this cosine function xt is equal to cos omega naught t, then yt is sine omega naught t, and we want to find the condition that these two signals are orthogonal to one another. Okay, so as I said, find the condition for the two signals to be orthogonal over the time period t. Then find the condition of approximate orthogonality if the above condition is not satisfied. If the first condition is satisfied, then the signals will be perfectly orthogonal. But even if it is not satisfied, under certain conditions, they will be approximately orthogonal to each other. For all practical purposes, you can consider them orthogonal. Okay, so let us see how to show this. What we have to do is to take the product of two signals xt and yt and then integrate over the time period t, and then find out the condition which will make this result of this integral equal to 0. So what we do, we substitute for xt and yt. So xt is cos omega naught t, yt is sine omega naught t, and then you integrate. Then you can use a trigonometric identity in order to change this to a slightly different form. So this is 1 by 2 sine of 2 omega naught t. This is one of the trigonometric identities. We use this so that integration becomes easy. So we now integrate this. So what we'll get is minus 1 by 4 omega naught cos of 2 omega naught t from the standard integration tables, and with the limits from 0 to t. So when we put the limits, this becomes minus 1 by 4 omega naught cos of 2 omega naught capital T, over which the integration is being calculated, and then cos of 0 is 1, so minus 1. Now these two signals are orthogonal to one another provided this result, which is the integration of the product, is equal to 0. If this is to be 0, the numerator must be 0, which means that this cos function must be equal to 1. So 1 minus 1, you will get 0. Which means that this angle, which is represented by 2 omega naught t here, should be an integer multiple of 2 pi for this to happen. So the condition, as we said, for this to be 0, 2 omega naught t is equal to 2n pi. You can write this as 2 into 2 pi f naught into t is equal to 2n pi, and which finally reduces to f naught is equal to n upon 2t. Okay, if this is satisfied, if this condition is satisfied, then cos and sine are exactly orthogonal to one another, which means that this integral is going to be 0. But even if this condition is not satisfied, then compare 4 omega naught with the maximum value of the numerator. Now you can see here this is minus 1. So when cos function is minus 1, you will get this as minus 2 with this minus sign. So maximum value of the numerator will be plus 2. Of course, here we are assuming that cos and sine both have unit amplitudes, but as long as their amplitudes are not too high, whatever we are discussing here, that result will be valid. So as long as 4 omega naught is much greater than the maximum value of the numerator, for all practical purposes this result will be negligible, and we can say that cos and sine functions are orthogonal to one another. And in most practical cases you will find that this required inequality is generally satisfied. So let me just state it again. Even if this condition is not satisfied, as long as 4 omega naught is much greater than 2, the integral value is negligible, and for all practical purposes you can say that cos and sine are orthogonal to one another. Next, we want to find the condition for the cos or the sine to be orthonormal. Okay, in that case, we need to consider some amplitude for cosine as well as sine. We'll first solve it for cosine. Similar results are available for the sine. Okay. So what we want to study here is the condition for the signal becoming orthonormal. So it's already orthogonal. Cos function is already orthogonal to the sine function, but we want to find the expression for its amplitude so that this integral is equal to 1. That will make it a normalized function. So remember, 0 to t phi t squared dt equal to 1, that was the condition. In this case, phi t is given by, say, a cos of 2 pi fct whole squared dt. So this has essentially, this integral has to be evaluated and equated to 1, and that will give us the required value for a. So the rest is just a little mathematical manipulation. So cos squared theta is 1 plus cos 2 theta by 2. So we change this, the whole thing becomes squared. So this is a squared, and we want this to be equal to 1. Now when we integrate this, there are two terms. One is a squared by 2 and the other is a squared by 2 cosine function. Now when you integrate a cosine function over a given time period, as long as integer number of cycles are over, you will find that the integration or the area under this cosine function is going to be 0. And even if they are not, it is not exactly an integer multiple it's not exactly an integer multiple of cycles. So in that case, as long as t is much large compared with the reciprocal of fc, for all practical purposes, we can say that when this cosine term is integrated, the result will be 0. So we can assume this to be 0. So the only thing left is now 1. And outside we'll get a squared by 2. 1 integrated will be t, and you put the limit 0 to t. So you will get a squared by 2, and then this 1 is t, so t minus 0 is equal to 1. Okay. So when you put the limits, well, I think there is a small error here. It should be t minus 0. Anyway, the result doesn't change. So a squared by 2 into t is equal to 1, which means a squared into t by 2 is equal to 1, or a squared is equal to 2 by t, or a is square root of 2 by t. So what have we shown? We have said that if we have a cosine function with an amplitude which is equal, which is given by this, then it's a normalized cosine function. That means if you square it and integrate, you will get 1. Actually, similar result can be easily shown for the sine wave, so I am not going through that, but the same result for the sine wave. So there also a is required to be under root of 2 by t. So what we have shown so far is that cosine and sine functions are orthogonal to one another, and if their amplitudes are properly adjusted, they can be called as orthonormal functions. And in our previous lecture, we have seen that by using orthonormal functions, we can generate various signaling waveforms. So again, let us see in the light of this how to generate various signaling waveforms. So remember, let's say S1T, that is the signaling waveform for one particular digital word, maybe 00 or whatever. So this will be S11. Remember, it was S11 into phi1. In this case, phi1 is root 2 by t cos omega t plus S12 into root 2 by t sin omega t. This root 2 by t sin omega t is phi2. These are your orthonormal waveforms. Now in literature, usually these are combined into a single value, and this coefficient of cos term is denoted by I and is called as the in-phase component, whereas the coefficient of this is represented by minus q and is called as the quadrature component. So this can be written as S1t will be equal to I1 cos omega t minus q1 sin of omega t. Whether you use a minus sign or plus sign is optional. You can use, as long as whatever sign you use at the transmitter, same convention is used at the receiver, you will not go wrong in detection. Okay, but here we are choosing minus. That is what is done in most of the literature, and we'll see the reason for that. Because if you represent this in the phasor form, the result that you will get will be I plus jq, which is a sort of a standard form. But just understand that minus sign here is not mandatory. You could have chosen plus. It is just conventional that most of the textbooks, most of the literature chooses minus. Okay. Now this was one of the signaling waveforms. So when you have another combination of binary digits, you have another waveform to represent that. So that is I2 cos omega t minus Q2 sin omega t. And in general, we can say ST is I cos omega t minus Q sin of omega t. In general, this is a general expression where I can be I1, Q can be Q1, or I can be I2 and Q can be Q2, and so on. Alright, so now whatever rest of the manipulation that we do, what we want to do is to find out the phasor representation for this, so that we can show a point in the phasor plane and show the constellation, various possible constellations. Remember, we had looked at the constellations last time, and we are now going to study it in terms of quadrature amplitude modulated signal, for which the equation is given by St equal to I cos omega t minus Q sin omega t. And now we want to show this in the phasor form. So for convenience, I have repeated this here. Now Q sin omega t can be written in terms of cos. The reason we write it in terms of cos is because whenever you want to write the phasor equation, you have to choose one reference waveform, and we are choosing cos as our reference. Therefore, we convert sine first into a cosine, and then we can write our phasor equations. So this remains as it is, I cos omega t minus Q, and sin omega t can be written as cos of omega t minus 90 degrees. So since cos is our reference, when we write this in the phasor form, I cos omega t term becomes I magnitude I with an angle 0, because this is a reference term, and Q cos omega t minus 90 degrees is Q with an angle minus 90 degrees. Okay. All right. So we'll continue this study further and obtain the complex expression for the phasor. So let us do this. I have again repeated this for convenience. I cos omega t is written in the phasor form with I with an angle 0, and Q cos omega t minus 90 is Q with angle minus 90. In that case, the phasor form for the signal S phasor is I with an angle 0 minus Q with an angle minus 90 degrees. And now we can convert this into rectangular form. So I cos of 0 is 1, sin of 0 is 0. So this is I into 1 plus j0 minus Q cos of minus 90 plus j sin of minus 90. So let us continue this further. I have repeated this for convenience. So the first term, now remember that cos of minus 90 is 0 and sin of minus 90 is minus 1. First term here is of course simply I, and then minus Q, this is 0 and this is minus 1, so this is minus j, this minus cancels and you will get plus. So the S phasor comes I plus jq. And we got this equation for the phasor because of the minus sign we had used. We'll get a different equation if we use a plus sign. But as I said, as long as you are consistent with the same notation for transmitter and receiver, you will not have a problem in detection of the signals. Okay, so this is your S phasor. So we can plot the constellation in the plane now with XY coordinates. So on the x-axis you can plot I, on the y-axis you can plot Q. Remember, in our last lecture we had plotted the coefficients of phi1 and phi2 etc. So we had got S11 etc. in the constellation plane. But most of the literature, instead of using S11, S12, they combine it with the scaling factor, and essentially use the coefficient of cos and sine rather than the orthonormal waveforms. So I plus jq. So the magnitude of this will be a will be under root of I squared plus q squared, and theta will be tangent inverse q by I. Okay. So polar equation, you can write real part of this, that is a cos of omega t plus theta. So in the constellation plane, you can show this on the x-axis. You plot the coefficient of cos, which is I. The y-axis you plot the coefficient of sine, which is q, and this is the constellation point. So I is called the in-phase component and q is called the quadrature component. Of course, we just showed this for just one signaling waveform, considering a general equation. But in actual practice, you have number of signaling waveforms. So you'll have number of values for each waveform. So first one you will get I1, second I1 and Q1. For the second you will get I2 and Q2 and so on. So let us look at that, considering all signaling waveforms. So S1t will have A1 cos of omega t plus theta 1, A1 amplitude and theta 1 phase. So this is like QAM signal is like a combined amplitude as well as phase modulation. So S2t will be A2 cos omega t plus theta 2. S3t will be A3 cos of omega t plus theta 3, and so on. So you can plot each one. For example, for S1t the phasor is S1 with an amplitude A1, angle theta 1, and this is the point which we have shown by star, and this is basically just a point, just to show that it looks like a constellation. We have shown a star here. So this is for the first, this is the phasor for the first waveform. Then you have the phasor for the second, so you can have third and so on, with different amplitudes and different phase angles. Now many different constellations are possible. I have shown only one possible thing, and what we'll do is we'll study what different QAM kind of signaling waveforms will generate different constellation waveforms, what are their properties and so on. But that is for the next session. In this session, we have essentially shown that cos and sine waveforms are orthogonal to each other, and you can generate signaling waveforms by using cos and sine, and we have seen how to show these waveforms in the phasor form and how to plot the constellation diagram in terms of I and Q. Remember, this is I and this is Q. So that is the rectangular form. This is the polar form, magnitude A1 and angle theta 1. And that's all in this session.